Alright, welcome back, ladies and gentlemen. We're in chapter 5.3, the day 1, trig equations. We're going to be solving trig equations without a calculator. Don't have a heart attack. Tomorrow is going to be with a calculator. Alright, well anyway, before we get going too far, the basic idea behind solving these equations here is going to be a little bit weird. How many x values satisfy the following equation down there? Sine of x equals 1. Okay, gut reaction, the answer is probably in your head 1. Alright, which would be right about there at pi over 2, so one solution for pi over 2, but wait a minute, what if I went around in a negative direction? So negative 3 pi over 2 would be there. But can't I, wherever I am, add 2 pi over and over and over and over and over again and keep getting to the same point on the unit circle? So consequently, it's not just 1 or 2, it's actually an infinite number of x values satisfy the following equation. Okay, basically the way we're going to portray this is saying x equals, okay, it's just more convenient to mention the positive value instead of the negative value, so I'm going to start with the pi over 2 here. Pi over 2, but, okay, again, the whole concept, I can go around the circle as many times as I want, so I can go 2 pi times around the circle, and what I'm going to do is slide a little n in there. And so 2n pi, we're going to assume that n is some integer value. So basically we can go some number of circles around and still get to the same spot and still have an answer that still qualifies as a solution for this equation. Alright, so basically this is what our answers, at least at some point, are going to look like. It's going to be kind of a starting value plus some multiple number of circles that you could put on there. Again, n is an integer, so it could be 0, so it basically wipes out that term and leaves us at the pi over 2, but then n could be 1, so giving us the pi over 2 plus one more complete circle, which would effectively be a 5 pi over 2, and then again, etc., etc., etc. Okay, and then the homework's over here just because I didn't have room later to do it. But let's keep rolling. Okay, now the equation I just demonstrated is basically the category I've got here facing you, trig equations with no restrictions. Later on we're going to restrict the solutions from 0 to 2 pi, but here we go from now. Okay, so if I've got no limitations on the x values I can use here, okay, I need to be able to accommodate that, and we're going to do that using that n pi sort of stuff that we just did, or technically 2n pi, but I'm going to change that for this one just to mess with you. Alright, anyway, here we go. Cotangent squared equals 1. Pretty simple equation. Not too many bells and whistles here. So, of course, first thing I want to do is square root both sides of this thing to cancel out the square. Okay, get my trig value by itself, and so now what I'm looking at is cotangent x equals, okay, don't forget the plus or minus on the 1. Okay, so at that point, our brains don't like cotangent very well, so realistically what I would do anytime I have a cotangent or one of the other reciprocal functions is I would just do the reciprocal of both sides of the equation effectively. In this case, that'll give me tangent x equals, well, the reciprocal of 1 is still 1, so in a very non-dramatic turn of events, I get tangent equals plus or minus 1. Okay, so from there, that's cool. And quite honestly, it really gives me two separate equations to consider. Tangent of x equals 1, and just for giggles, let's change the equation's color here, and get tangent x equals negative 1. Alright, well, for tangent x equals 1, okay, well, thinking of my all students take calculus kind of setup, and tangent 1 being at a pi over 4 reference angle, basically that means that my tangent is going to be right about here at pi over 4, but additionally down here, I get a tangent value of 1 in the third quadrant and another pi over 4 reference angle. So that's going to be 5 pi over 4, but we'll get to that later. Okay, taking a look at the negative 1, okay, since I'm still at a 1, I'm still at a reference angle of pi over 4, it just lands me in the fourth quadrant and the second quadrant. Okay, so I get that kind of a setup. Okay, again, notice that pi over 4 is a 45-degree angle for those of you not thinking well in radians yet. And so if it's 45 up from here, 45 up from there, that leaves a nice right angle here of 90 degrees, or pi over 2. And again, that pattern basically goes all the way around. So I could go with two separate x equals statements that have some kind of a pi attached to them at the end with an n attached to it, but because of the convenience of what happened here, let's pick another color for this. Okay, I can basically start here at the pi over 4. Okay, and then since it is a nice consistent measurement from one solution to the next as I keep going around the circle, I can basically just say that pi over 4 plus n pi over 2's, which will continually get me from one of these reference angles that I like to the next all the way around. So basically there's the most simplified way of writing the answer. Okay, again, in case you're really just dying to know, the kind of not very nice way to write this would have been x equals that pi over 4 plus, if I want to go from this blue to the other blue, I'd have to go a complete pi way around. Okay, hopefully that's not too much of a shock because the period of tangent is pi, so wherever I am for one tangent value, in general, going pi away it will land you on another one. Okay, I could take that one, but then I would have to take the other one for the greens and do x equals, okay, my first smallest positive measurement over here is at 3 pi over 4. And then again, to get from this green one to the other green one, I'd have to go some number of pi's again. Again, 1 for the first one, but then I could go 2 pi's, 3 pi's, etc., keep bouncing around the circle. So you can give me an answer that looks kind of like this, but quite honestly, this is kind of messy and icky, as the red one is a little bit more nice and happy and wonderful. So yes, in a situation like this, I would much prefer the red here versus the blue-green combo. Okay, let's take another one of these with the no restriction policy in effect. Alright, so cosecant squared plus 2 cosecant x equals 0. Okay, well, kind of think back to equations you had that were like u squared plus 2u equals 0. If I had something like this, my first step would be to factor out the u, and that's basically what's happening here. Thinking of cosecant as my u value, if you will. So anyway, I'm going to factor out a cosecant, okay, and so that leaves me with cosecant plus 2 equals 0, and just like this sort of setup, after you get things factored, you just set each factor equal to 0. So that's basically all I'm going to do here. So now cosecant x equals 0, and then cosecant x plus 2 equals 0. Okay, now we can play the color game here, but whatever the case, again, this is one of the nasty ones, so I don't like it. I'm going to turn it into its reciprocal. So doing so leaves me sine of x equals, well, the reciprocal of 0 is undefined. So there we go, undefined, but hey, sine undefined, well, that never happens. So since that never happens, we basically can throw out that half of the equation. Okay, so let's focus on the right half, basically. Okay, this guy we do have a little bit of cleanup to do. So we get cosecant x equals negative 2. And then again, doing my reciprocal sort of trick here gives me sine of x equals negative 1/2. Well, that definitely does happen. Those are nice unit circle values. So I'll go over my kind of little sketch here for unit circle and figure out where the heck that happens. Okay, again, sine being negative puts me down in the third and fourth quadrants, and at a negative 1/2 gives me a reference angle of pi over 6. So basically I have the skinny angles, if you will. Okay, so that'll be 7 pi over 6 right there, again just wrapping around in the positive direction. Remember, we can also do this over here in the fourth quadrant, and doing that gives me another reference angle of pi over 6, but in this case the actual measurement is 11 pi over 6. Again, you can consider that negative pi over 6 if you wanted to, but quite honestly, when you're checking your answers in the book, what they're going to do is go with the positive measurement somewhere between 0 and 2 pi as your sort of starting value, if you will. And what I mean by that is this 7 pi over 6 is going to be my starting value. So as far as my x's, I've got 7 pi over 6. Okay, now with the last one I had a very convenient sort of measurement that led me from one to another, and I could repeat that measurement and it would keep bouncing from one solution to the next. Okay, notice here, if I go whatever the measurement is to get me a 7 pi over 6 or an 11 pi over 6, okay, notice it's less than half the circle. Okay, in order to get to the next one, I have to go more than half a circle. So it's not a nice even measurement, so I can't kind of compress this into one solid answer. So basically, and again, based on the fact that sine has a period of 2 pi, hopefully it's not too big of a shock now, that I've got 7 pi over 6, and there's no nice way to do this other than go all the way around the circle. So I've got some number of 2 pi's to get myself back around to that solution again. Okay, and the same basic idea, starting at that 11 pi over 6. Okay, again, there's no nice measurement that takes me to the other guy, so I have no choice but to go completely around the circle. So again, that's 2 times n pi's. That again is another trip around the circle to get from one to the next. So basically there's what the final answer to that particular equation would be. Okay, as I mentioned earlier now, we've got kind of a set of problems here. Let's find all solutions in the interval 0 to 2 pi. Okay, so the bad news is that since these are locking us into a particular interval, so basically one trip around the circle, in general these equations are a little bit nastier to deal with. Okay, although do notice that the 0 has a bracket and the 2 pi has a parenthesis on it, so if I do have a solution that is right here on the 0.10. I'm going to call that 0, and I'm not going to call it 2 pi. So just kind of a splitting hairs thing there, but just pay attention to that in case it does happen. Okay, so anyway, looking at this, I've got 2 sine squared, and I've got cosine plus 2. Okay, well, it's a little bit awkward having two different trig functions, but through the magic of our various trig substitution possibilities, I can turn sine squared into something with a cosine. So basically that's what I'm going to do here, to kind of clean up our mess we have. So 2, and instead of sine squared, I can turn that into 1 minus cosine squared. Alright, and again, just copying the rest of that equation. Okay, I'll distribute the 2, because quite honestly, anytime you see something in front of a parenthesis, that's pretty much what you do. Alright. Okay, now a couple convenient things happen here. One is I can cancel out the two 2's. Basically subtract 2 from both sides, and those two guys just go away. Okay, now I've got this negative 2 cosine squared equals cosine. So what I'm going to do is I'm going to kind of move this guy to the right side of the equation and get myself a 0 equals 2 cosine squared plus cosine as my equation. And like I did in a previous problem, okay, we can factor out a cosine now because it's kind of a common factor. Alright, so that comes out, and I'm left with 2 cosine x plus 1. And then, well, I can break that into my two equations, so I get 0 equals cosine, and then I get 0 equals 2 cosine plus 1. Okay, this guy's already solved, but I'll kind of mess with this guy a little bit more. Alright, basically, if you let me get away with this, I'm going to subtract 1 and divide by 2, so that's going to give me a cosine x equals negative 1/2. And just because this is a little awkward, I'm going to rewrite this as cosine x equals 0. Okay, now, I'm sure everybody's feeling a lot better about life in general now that I've done that. Okay, well, so let's just take a look at where on the circle cosine would be 0. Alright, so cosine x equals 0, again, that's my x-coordinate for cosine. So where's my x 0? Well, that happens right there, and it happens right there on the unit circle. Okay, so cosine negative 1/2, again, since I'm looking at my x-coordinates, I'm looking at a reference angle here of pi over 6, and it should be, vaguely sitting at about there. Again, just do your best, and an approximate angle will hopefully get the job done here. And again, pi over 6 over there. I'm sorry, pi over 3 reference angles. I might have misspoke there. I apologize if I did. Alright, so there we go. And so basically just list what those are. And the order that you list them in doesn't really matter, but here we go. X equals, I'm just going to go counterclockwise around the circle. So this first guy, that's pi over 2. Okay, and then again, if I'm at a pi over 3 reference angle, that's going to get me a 2 pi over 3. Okay, wrapping my way down here in the third quadrant is going to give me a 4 pi over 3. And then finally making it straight down, if you will, is a 3 pi over 2. So there's my 4 angle measures that will satisfy that equation within the range of, or sorry, the domain of 0 to 2 pi. Alright, well, hopefully everybody's very excited about that one. Let's do one that's even worse. Alrighty. Okay, now we do have a problem here with this one. This equation does get kind of hairy, as I said a second ago, but here it is. Okay, I've got 2 cosine x plus 3 tangent x equals 0. Okay, well, again, I have the very bad sort of arrangement of two different trig values, or trig functions, although the worst news is that I can't directly turn one into the other. Okay, so really, I'm kind of a little bit stuck there. So again, let's just start playing. Okay, so 2 cosine plus 3, well, tangent I can turn into sine over cosine. So let's do that. Sine over cosine. Alrighty. Okay, well, hey, that's got a fraction in it now. So, hey, let's get rid of that fraction. So we're going to multiply both sides by cosine. Okay, now I'd like to take a moment here and say, hey, I'm not verifying an equation right now. I'm trying to solve an equation, so I'm very free to do anything I want to both sides. What I don't want to do, though, is divide off a trig function, because basically what that'll do is divide off answers. Okay, but multiplying both sides by a trig function is going to preserve those answers in general, and so that is something that is allowed. Just don't divide them off, because that basically loses solutions, kind of like dividing both sides by x in an equation. Sometimes you lose solutions by doing that as well. Okay, so I digress. Here we are again. Okay, so multiplying through by the cosine gives me 2 cosine squared x plus, again, the whole point was canceling out the cosine here, so this is just 3 sine x equals 0 times cosine is still 0. Okay, so I'm in a little better shape now, because now I have a cosine squared and I have a sine, and I can turn cosine squared into sine. So let's do that. 2 parentheses 1 minus sine squared. Okay, those Pythagorean identities are very, very useful. 3 sine x equals 0. Okay, well, here we go. Little distribution. 2 minus 2 sine squared x plus 3 sine x is still equal to 0. That 0 is getting very, very bored over there. Okay, but now I've got a little bit of a mess here to clean up as well. Okay, no like terms, but what I do have is a negative squared guy. And I don't know, just me, I don't like having a negative squared guy if I can help it. So basically what I'm going to do, and you can handle this one of two ways. Either imagine moving every single one of these terms to the other side of the equal sign to generate the positive value on your squared guy, or think of dividing everything by a negative. Okay, so whatever the case for you, basically what I'm going to end up with now is a positive 2 sine squared x. I'll have a negative 3 sine x, and again, in case I didn't mention it, I'm now rewriting this thing in descending order, and then I've got a minus 2. Okay, now that's kind of a trinomial sort of setup, so hey, maybe that's factorable. And yes, it is. So I can factor this into 2 sine x, close the parentheses, get a sine x right there, close the parenthesis again, have my equal 0, and I just got to break up the 2 in such a way to make a 3. Well, by putting a 2 over there and a 1 right there, a negative on the 2 and a positive on the 1, I get something that will FOIL back out to give me the step ahead of me, so I'm feeling good about life in general again. Okay. So now again, breaking this into the two equations. Okay, for space concerns, I'm just going to call this sine x equals negative 1/2. Okay, if I lost you on that, definitely ask me in class, and I'll be happy to explain what happened. Same thing basically here. I'm setting this equal to 0 and solving it. So sine of x equals 2. Okay, now sine of x equals 2. Remember, sine just kind of oscillates between -1 and +1. So again, here's another one that doesn't happen. So we can switch over to our magic red pen and basically just cross that guy out, because this guy plain old doesn't happen. Woohoo! So I'm sure you're glad to hear that the work is less. Alright, then we got sine is negative 1/2, and that happens in a few places in the circle, well, specifically 2. Alright, so again, my y value being negative 1/2, reference angle of pi over 6 will put me about right there for a y value of negative 1/2. And of course we're talking about sine, we're talking about y value, so it'll happen also in the 4th quadrant, like it did in the 3rd. Okay, so as a final answer, again, I'm still in the interval from 0 to 2 pi. So I want to start at 0, wrapping myself around in a positive direction until I get to here, and then it's going to be 7 pi over 6. And as I continue it over to here, that gives me an 11 pi over 6. And again, since I was restricted, I don't have to include any of that n pi stuff. So there are my two answers to that equation. And another thing I'd like you to be able to work with is having multiple angle equations, and we're going to find all the solutions. So basically what that does mean is we're going to have that n pi kind of stuff going on. Alright, so anyway, sine of 3x equals root 3 over 2. Well, you might be like, hey, what the heck is going on here? Well, basically what you can do is, well, since 3x is icky, well, let's replace it with something that's not icky. So I'm going to let 3x equals, I like to use a capital letter A. You're free to use anything you like. If you like using the U, that's great. If you like drawing a fuzzy bunny and using that in its place, whatever. But just do some sort of replacement, or if you're comfortable with a 3x after you watch me do this and said, oh, I could have left the 3x in there, then that's great. Okay, but anyway, so what's happened now is we've got a slightly modified equation, sine of A equals root 3 over 2. Okay, well that one's not so bad because those are nice unit circle values and they're positive, so with sine, positive values leaves me on the top half of my unit circle. And the root 3 over 2, well, that's my y value being big, so that gives me my pi over 3 reference angles. So basically I'm looking at that and like that. Okay, so basically pi over 3 and then 2 pi over 3. Okay, so basically that's what I have here as a solution. So A has got to be my pi over 3. Okay, again, since I'm not restricted to 0 to 2 pi, I have to consider how I can get around from there to another angle that makes sense. Again, I can go here, but then obviously that's not an even split to get back around, so I can't cut it in half or anything crazy like that. I have to go all the way around the circle. So pi over 3 plus 2n pi again. Again, that represents 2 pi n times. So there's one of my possibilities, and then I do have another, is the 2 pi over 3. So basically, A equals 2 pi over 3 plus 2n pi again. And that's all well and good, but I really don't care about A, I care about x. So basically now, going back to blue, replacing my a's with 3x's gives me two equations. I've got 3x equals pi over 3 plus 2n pi. And then, let me just do this horizontally here, 3x equals 2 pi over 3 plus 2n pi. Okay, well, honestly, if I don't even pay attention to what's on the right side of this equation here, If I have 3x equals something, and I want to solve for that, well, of course, one thing I can do is divide everything by 3. So I'll divide both sides by 3, and get myself an x by itself. Woo! Alright. Well, now pi over 3 divided by 3 is pi over 9. Well, not the end of the world, but something we're not exactly used to. And same thing here, 2n pi divided by 3, well, it doesn't reduce, so just leave it as what I just said, 2n pi over 3. Okay, so there's one set of an infinite number of answers. And then we can do the same thing over here, simply dividing off the 3, oops, on all 3 sides. Sorry, that's a little bit sloppy. Please don't hurt me. Okay, we've got that, and so the other possibility for x is going to be 2 pi over 3 over 3, better yet, 2 pi over 9, plus, same thing over here, 2n pi over 3. So it is a little bit messy looking, but picking any appropriate n value, simplifying the mess that shows up, and then plugging back in the original equation will in fact give you a valid answer. So basically that's how you handle the multiple angles equations. Hopefully that wasn't too much of a pain. Again, ask me in class for any sort of clarification necessary. I know this is not the easiest thing I've ever tried to teach, but there it is, and I'll see you in class.